Pretend for a moment that you're in the doctor's office and you're there because you are observing a doctor as he does his work throughout the day. Now let's say that this doctor is seeing a patient and that particular patient is having some kind of heart trouble. So the doctor decides to order an EKG in order to better understand how the patient's heart is working or not working. So you might expect the EKG tracing to look something like this, because a diagram like this is what you would often see if you were to take a class and learn about EKGs, or if you were to just look up this information on your own. But when the test results come back, the doctor actually is holding something in his hand that looks more like this. Now, why does this chart look so much more confusing than the simple textbook drawing that we see on the left? To answer this question, we need to understand how exactly the whole system of taking an EKG and getting the recording is actually set up. So let's go to a situation that's a little bit simpler. Let's say we have a box, and inside of the box are some charges, and the charges are moving around. But now let's say that we don't actually know what is happening inside of the box. So we know the charges are there, but we just don't know which way they're moving. So this situation is actually kind of similar to what happens when you have a patient who has heart trouble. You know that their heart is beating, and the reason the heart's beating is because of motion of electrical charges inside of the heart. But we want to know more about how those charges are behaving and how the heart is behaving electrically in general. So how are we able to figure out this puzzle? Well, what we can do is we put charge sensors on the very edges of the box, and those charge sensors are called electrodes. Now, I've drawn two electrodes here because electrodes come in pairs. The first member of the pair in green is called the positive electrode, and then the second member of the pair in red is called the negative electrode. Now, how do these electrodes actually work? Well, let me draw an arrow between the electrodes in blue, and the arrow is going from the negative electrode to the positive electrode. And this arrow indicates the path of a hypothetical charge if it were to start right from the positive electrode and travel all the way to the tip of the negative electrode. And if that charge were to move in that exact path, the electrodes would get very excited and report a reading, and that reading is in the form of a voltage, and the voltage would be very high. Now this blue arrow, because it has a distance and a direction, is called a vector. And in physics we learned that all a vector is some kind of distance with a directionality to it. And it turns out that how well charges' paths align to the vectors that exist between electrodes determines how excited the electrodes get when they sense that charge moving around. So in this case, since the charges are moving in a direction that's parallel to the blue vector, there's going to be a positive deflection or change in voltage when the voltage reading comes out. But if the charges decided to move in the opposite direction, like so, you would expect the voltage tracing to go downwards, like this. And if the charges decided to move in a direction that's perpendicular to the blue vector, like so, or like so, pretend that's a 90-degree angle, then you would see no change in voltage because the path of the charges in green has no component that has anything in common with that path that exists between the electrodes, which is in blue. So let's think a little bit about what that would mean in a real heart. So let's say you have your heart and you place your electrodes on either side of it like this, and then you place your vector between the electrodes. And now let's say you've got positive charges moving from one side of the heart to the other, like so. So you can see the direction of charge motion is actually parallel to the vector that sits between the electrodes. And the way I've set this diagram up is so that the charges are moving in a direction that is seen in a healthy person. So that would mean you're going to see the maximum level of excitement in these electrodes. And so you're going to see a positive voltage, a nice strong positive signal. And again, the y-axis is voltage and the x-axis is time. But in disease states, this isn't always the case. That is, the charges don't always move in that nice, healthy direction. And so we have to consider all the other cases in which the charges are moving in the wrong direction. So what would that look like on a voltage tracing? So I'm going to walk you through that. So imagine that we've put our electrodes in exactly the same places. And so our blue vectors are all going to look the same again. And now our pink vector, which represents how charges are moving inside of the heart, can change. So let's draw in various directions that the charges could go. So in this case right here, we would see that the direction of charge motion is it has some kind of component that's parallel to the blue vector. So there's something in common with it, but it's not completely in the direction that it's supposed to be in. So the electrodes are going to get some kind of excitement, but it's not going to be nearly as overwhelming as what we saw in our first instance right here. So our signal would look something like this. So there's some positive amplitude, but it's not as high as in the first case. Now let's say we go to this situation where our charge is moving in what was supposed to be a 90-degree angle, if only I could draw well. And so in that case, the direction of motion of charge has nothing in common with the path that's between the electrodes. So we would see no change in voltage, or a very minimal one, if at all. And now we get to these two cases where the direction of charge is actually moving in the opposite way that it should be in the healthy state. So in this situation, we have our charge moving in exactly the opposite direction as the positions of the electrodes. And so we would imagine that our deflection on the voltage tracing would be massive and massively downwards. And if we were to go to this middle case, pretty similar to this second case right here, except that it's in the negative direction. So we see that our charges are moving in kind of a way that is opposite to the blue vector, but it's not completely aligned. So we're going to see some kind of negative deflection, but not as strong as in the last scenario. So now you can really see how electrodes work. They detect how well charges' motions align to the vector that sits between the two electrodes. And in that way, they can really figure out how charges are moving around inside of the heart, which can tell you a lot about whether the heart is healthy or not. Now, applying this concept of using pairs of electrodes to detect moving charges to a patient in order to get an EKG tracing, you might expect that you could put two electrodes on the patient's body and use them to detect how the heart is behaving electrically. And that would be just fine, and it would give you some information, but doctors like to have a lot of information. And so what they do is, pretend this circle represents our patient, they would want not just one set of electrodes like this, but they would also like to see another set of electrodes like this, and another set of electrodes like this, and so on and so forth, until they had a bunch of different pairs that could read out different kinds of information. And using all of these different electrode pairs, the doctor would be able to get a very, very accurate picture of how charges move around inside of the heart, what direction they take, and so on and so forth. Now, it gets really cumbersome if we're dealing with so many pairs of electrodes, and so doctors like to use a different term for a pair of electrodes, and that term is called lead. And all a lead is one pair of electrodes, one being positive and one being negative. And it turns out that when an EKG has to be obtained from a patient, 10 electrodes are placed on the person's body, and these 10 electrodes are combined in various ways to construct 12 different leads, or 12 different pair combinations. And since each pair of electrodes can be thought of as having a vector that runs between it, we can actually consider each lead to be a vector. And so then all an EKG tracing is a readout of how well different charge motion vectors, or directions of charge moving around inside of the heart, align to each of the different leads. So that is the general idea of how EKGs work. But now I'd like to talk more about the details of how the setup actually works, because this is pretty important to understanding what you're seeing on an EKG tracing. So here's a diagram of a person. And again, we have 12 different leads that we're going to eventually have. And these 12 different leads, again, come from 10 different electrodes. And here are where the electrodes actually fall on a patient's body. So in blue, I have electrodes that are placed on a person's limbs. And in red, I have electrodes that are placed on a person's chest. So if you count them, there are 6 chest electrodes in red and 4 limb electrodes in blue. And it turns out that when we combine these different electrodes into various pairs, when we get our 12 different leads, they actually fall into 2 groups. And the first group is called the limb leads, and these are made entirely from different combinations of the blue electrodes. And the second group of leads are the chest leads, also known as the precordial leads. And these leads are made entirely from different combinations of the red electrodes on a person's chest. Now I'm going to go on and talk a lot more about each of these different groups of leads, but before I do that, I'd like to draw your attention to the light blue electrode, which is sitting on this person's right foot, which is on the left side of the diagram. This electrode is used to designate ground. So it's a reference point on the person's body. It's not used to construct any of the leads, and it's there to minimize interference in any of the signals. But otherwise, it doesn't do very much for us. So now that we understand that, let's think in detail about how these different sets of leads are made. So let's talk about the limb leads first. Here is the person's body again. And now what I've done is drawn in the 3 different electrodes on the patient's limbs that are used to make the limb leads. That's why they're called limb leads. So these 3 electrodes are responsible for the 6 limb leads. And how do you construct a limb lead? Well, the first 3 limb leads are pretty easy. All you have to do is draw an arrow from one electrode to the other. And the arrows look like this. Now there's the rule that an arrow has to go from a negative electrode to a positive one. So here's our negative electrode, and here's our positive electrode. The arrow is going from negative to positive. And here's our negative electrode, and here's our positive electrode. Again, the arrow is going from negative to positive. But when we get here, at this particular electrode, and we're trying to account for this particular vector, we run into a problem. And that problem is that the electrode right here is positive already, but we want it to go from negative to positive. And actually, it turns out that electrodes can be considered to be either positive or negative depending on the circumstances. So because of our technology, we can pretend that one electrode is positive in one instance, and then go on to the next instance and pretend it's negative. So that's kind of nice. So now we have 3 different arrows, and each of those arrows is a vector. And that vector is describing a lead. And each of these leads has a name. The lead that's going from left to right is called lead number 1. And then the other 2 leads are called lead 2 and lead 3. Pretty simple. And these 3 leads are called the bipolar limb leads. And this is probably because they're limb leads. They come from electrodes that are placed on the person's limb. And when they say bipolar, it means that one electrode is negative and the other is positive. Now you'll notice here that the bipolar limb leads together form a triangle on a person's body. And that triangle actually has a name. It's called Einthoven's triangle. And that word is pretty famous, but all it really means is leads 1, 2, and 3 together. So we have our 3 first limb leads, and that's great, and we understand where they come from, but we still have 3 more limb leads to account for, and making them is actually not quite as simple. So what I'm going to do is walk you through each of them, and the first one I'm going to describe to you is called AVF. And how you make AVF is you decide where your positive electrode is, and the positive electrode in this case is right on the patient's foot. But when you're trying to figure out your negative electrode, that's actually the trickier part. So it's actually not either one of the hand electrodes. If so, we would just get lead 2 or 3 all over again. Instead, it's a combination of the two. So you actually average the input of the 2 electrodes to come up with sort of a hypothetical negative electrode. And the way you do this is, if you were to draw a line between the 2 remaining electrodes like so, you would find the midpoint of that line, which is somewhere over here. And then you would pretend that that the spot that's in the midpoint is where your negative electrode is. And then you would draw your vector going from this negative electrode down to your positive one. And there you have AVF. And a good way to remember it's called AVF is that the F stands for foot, because the vector that composes AVF points directly down at the patient's feet. So the next 2 leads are constructed in a similar manner. They're called AVL and AVR. And so for AVL, you decide which electrode is your positive electrode first, and that would be the patient's left hand, which is on your right side. And then the negative electrode is the average of the 2 remaining electrodes. And so if you were to draw your line between the 2 electrodes, you would find your midpoint is somewhere here. And so this is your imaginary negative electrode, and therefore you would draw your vector going from the negative electrode to the positive one like this, and there you have AVL. And AVR, similarly, is where you have your positive electrode right here, your negative electrode being the average between the 2 remaining, and then you can draw in your vector like this. And I keep the names of AVL and AVR straight by saying the L stands for left hand, because the vector is pointing to the patient's left hand, and AVR, the R stands for right hand, because the vector is pointing at the patient's right hand. So those are the 3 remaining limb leads, and because they're made with the negative electrode coming from an average between 2 other electrodes, they're given a special name, and that is the augmented limb leads. Augmented because there's some addition involved in their construction. So that is a lot of leads to remember. And so what I'm going to do is recap them all here for you so that they're in one place. So again, the first lead, lead 1, is here. Then we have lead 2, then lead 3, and then we have our augmented limb leads, which are AVF, then AVL, and then finally AVR. And this can seem kind of scary, but you can appreciate that because the arrows are pointing in all different directions, there are many different viewpoints about which we can look at the heart's electrical activity. And so the heart could have charges moving in many different directions, and if it's moving in a certain direction, it's almost certainly going to overlap with one of these leads and get at least one of them to become excited. So that's very good. Now, doctors like to organize their thoughts about the leads in a different way, and what they do is they see how the leads are on a person's body, but then they kind of plot how the leads look on an axis. So if you were to imagine a circle and you imagine an x-axis and a y-axis, they plot the leads on an xy coordinate sort of basis. So lead number 1, which is going from left to right, if you were to start it at the origin, it would go like this. And then lead number 2, if you started that at the origin, like so, then it would be going down at about a 60-degree angle like this. Lead 3, similarly, if you started it at the origin, it would be going down at about a 120-degree angle, and AVF in blue goes straight down at about a 90-degree angle, and we can plot all of the other vectors onto our XY graph like so. So if you imagine the heart to be at the origin of this graph, then you could imagine that each of these vectors represents all of the different angles at which we can look at the heart. And the reason doctors like to organize their thoughts on graphs like this is because it really helps determine what the angle of their different viewpoints are for each lead. And this becomes really important when there are charges moving around inside the heart and you want to determine at what specific angle they're moving across from one side of the heart to the other. So if they're moving, say, at a negative 150-degree angle, that would mean that if this was your heart, charges are moving in this direction. And as we know, that's probably not a good thing if we want the heart to depolarize from here to here, which is normal physiologically. And so a pie chart like this can help a doctor to really figure out whether charges are moving in the right direction at the right time. So that is our summary of the limb leads. Now let's move on and talk about the 6 other leads in the other group of leads that are used to make an EKG, and those are the precordial leads, also known as the chest leads. So they're made from the electrodes that are drawn here in red. The interesting thing about them is all of these electrodes are actually positive electrodes. And all of the negative quote-unquote electrodes are actually reference points on the patient's back. So that would mean that if you were to look at this diagram, the vector going from the negative electrode to the positive one would be coming out at you from the screen. So to kind of show you what I mean in 3D, I'm going to do a little bit of an animation. So let's say you cut the patient like so with the dashed line, and you get rid of the top part. So now you're looking at a cross section. I know that's a bit gory, but just bear with it for a bit. So if we were to draw in what you would see in the cross section, you would kind of also draw a slice through the heart. And so there are all of these leads sitting on the patient's skin out front. And then farther in the back, you've got a slice of the patient's body, and the heart is sitting somewhere in that slice. And then right here, this line in the back is the patient's back. So if we were to kind of blow up this image of the cross section and turn it on its face so that now here is the person's back and here's the person's front. So essentially what you've done is you've taken that cross section and flipped it so that it's now lying on the page flat. What you would see is here are all of the electrodes, the precordial or chest electrodes, and they are all positive. And then we imagine that the entire backside of the patient is negative. So this is all negative. And so how you construct each of the chest leads is you actually find a reference point inside of the heart, and that reference point is somewhere here. It's actually the AV node or atrioventricular node. And then you draw your vector from the negative backside of the person to the positive electrode through the AV node. So my artwork is rather questionable, but all of these vectors should be intersecting at the AV node. And so this is what our precordial leads look like. Now I should tell you what the leads' names are, and they're actually quite simple. The leads are called V1 through V6. So it's V1, V2, V3, V4, V5, and then V6. So that's essentially all there is to it for the precordial leads. But one thing you might be confused about is how the precordial leads and the limb leads make sense together in 3 dimensions on the person's body. It is a lot of leads to account for, and so what I'd like to do is kind of walk you through how the leads fit in 3 dimensions. So what I've drawn here is 3 different planes that run through a person's body, and in medicine there are actual names for these planes. So the plane right here is called the sagittal plane. This is called the coronal plane, and this is the transverse plane. It turns out that no lead runs in the sagittal plane. There is no vector in the sagittal plane when we're trying to record an EKG. So from now on, we can just not care about this one. But The limb leads actually lie in the coronal plane, like this. And the precordial leads lie in the transverse plane, like this. And I haven't drawn all of them, but you kind of get the idea. They all run in this plane, and they're sort of splaying out of the person. It's as if a bunch of arrows is coming out of her body. But the point of me telling you this is to help you appreciate that if we have leads in two different planes, we've essentially got electrical activity mapped out in both the coronal and the transverse plane. So we're looking at the heart in 3 dimensions. So that is essentially all of the information that you need to set up an EKG. You now know that there are 12 leads, there are 6 limb leads in the coronal plane, and 6 limb leads in the transverse plane, and they're picking up the heart's electrical activity in 2 different planes so that we get a sense of how the heart is acting in 3D. So now what I'd like to do is go back to a diagram that I showed you way at the beginning of this presentation. It looks like this. And this is what an EKG tracing would look like if we got it directly from a patient. And remember that the textbook drawing of an EKG tracing looked like this. So what I'd like to do now is address the question that we started out with. How do we go from this simple textbook diagram of an EKG tracing, like here, and turn it into something like this, which comes from an actual patient? So the squiggly black line that you're seeing in the diagram of the EKG from the real patient is the voltage tracing, or the change in voltage that different leads are picking up. And you'll notice that above this squiggly black line are some letters and numbers, such as right here, 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 so on and so forth. And you'll notice, if you look carefully, that these letters and numbers are actually the names of the leads that we just talked about. So if you look on the left, you'll see leads 1, 2, 3, AVR, AVL, and AVF. Their names are all here. And it turns out that if you draw a line through the center of this EKG, all of the limb leads are on the left, and then the names of all of the precordial leads are on the right. And it turns out that our squiggly line is divided into sections, and each section is devoted to the lead that is written next to that part of the squiggly line. So what I mean by that is, say we look at the section that's labeled by V1. It goes and it starts from here and it ends right here. So the span of the voltage tracing that is devoted to lead 1 is right here. So this squiggly line going from here to here, and it ends right here, is the voltage that would result if we were looking just at lead 1, and what electrical activity would it report. And then we can do the same thing for lead 2. It goes from here all the way to here. And lead 3, which goes from here to here, and so on for all of the different limb leads. And then the same thing is done for all of the precordial leads. V1 goes from here to here, V2 goes from here to here, and that's the way it goes for all of them. So this might explain to you something about why our EKG tracing looks different from our textbook diagram. It's generally a lot longer, and that's because there are tracings that are accounting for each of the 12 different leads. But then you can kind of look at this diagram and say, well, the squiggly black line I'm seeing doesn't really follow the pattern that I'm seeing here from the textbook diagram. And what I'd like to show you is that for some of the leads, it actually does follow that pattern. So let's say we looked at lead 1, and lead 1 goes again from here to here. And what we see is that there are 3 peaks in this particular span of paper, and the 3 peaks actually represent 3 cardiac cycles that got recorded before the lead switched over. So if we were to mark out 1 cardiac cycle, let's say we pick this wave. So this span right here is 1 cardiac cycle. And if we were to compare the voltage tracing from this 1 cardiac cycle to the one found in the textbook, we would actually see that there is a lot of overlap, and there's actually the same elements in this one tracing that there are in the textbook version. So to show you what I mean, here is a small hump that starts off the cardiac cycle, and that small hump can be found here in our textbook diagram, and this is actually the P wave. And then we have a tiny dip. It's almost invisible, but you can still kind of see it. And that dip kind of matches up with this dip, which is the Q wave. And then we have a large spike, and that spike is the R wave, and it corresponds to this, which is also an R wave. And then in this particular tracing, you see that after the R wave, the curve becomes a flat line. But then if you go back to the EKG tracing from the textbook diagram, you'll see that there was supposed to be a dip after the R wave that was supposed to correspond to the S wave. So it seems like for our particular diagram, there is no S wave. And then we see a larger hump right here, and that is the T wave, which also corresponds to this larger hump, which is also a T wave. So all of the essential elements are basically there, and it's repeated over and over again in lead 1. And if you go to the different leads, you're going to see essentially the same pattern, but with some minor variations. So let's say you went to lead 3, which is right here. You would say that there's a P wave, you don't really see a Q wave, then there's an R wave, and then an S wave, and then there's a T wave, and that's one cardiac cycle. And the reason lead 3 looks different from lead 1 is that lead 3 is running in a different direction than lead 1, and so it's going to pick up a different kind of activity. Now there are a few like AVR and V1 and perhaps even V2 in this diagram that you kind of look at it and say, I'm not really seeing what I'm supposed to be seeing. And that's actually okay. It's just that various parts of the diagram are distorted. So let's say you were looking at V2 and you're thinking, how does this diagram match up to that one? And really the reason it looks so different from the textbook version is that the different humps, depressions, and peaks in V2 are actually distorted versions of what are found in the textbook diagram, but they're basically all still there. You have your little hump, that's the P wave. You're missing your Q, but that's often the case in many of the leads. You have a small R wave, and you have a very, very deep S wave, and you have a very large T wave. But all of the elements are essentially there. And so thinking about distortions of the different elements kind of helps you to see what's really there. Now for right now, let's not worry about these different variations in how the EKG tracing could look from lead to lead, but just know that the different patterns that exist are what tells a doctor whether the patient is healthy or not.